video, we are going to discuss the laws of the exponents and the logarithm. So first of all, let's talk about the laws of the exponents. So if n is a positive integer, then an is the product of n factors of a, or we can write it as a to the power of n, and a to the power of n is same as the multiplication of the n numbers of the a. Okay, so when you have a to the power of n, let's rewrite this on the right hand side. We say that a is the base, n is the exponent, or we also say exponent or power or index. However, for the purpose of this class, we're going to use the exponent as our common term. Okay, so therefore, it is possible to derive this law of the exponents. Okay, the first one that we're going to discuss with this section is the product rule. So when you have a product rule, if we have x to the power of m times x to the power of n, we calculate the total number of the exponents by adding up the exponents. Okay, the quotient rule means when you have cases like this here, or like exponent or over another exponent, right? Then we actually subtract the lower exponent from the upper exponent to find the summarized version. And the zero exponent rule means if we have 0 as our power or the exponent, it always equals to 1 despite what kind of number you have as a base. However, you cannot have 0 as base. Okay, the power rule means if we have exponent and another exponent outside of the bracket, like in this case, we multiply these two exponents together to find the total number of the exponent. And there's something called expanded power rule, means that we can expand the exponents to calculate the expanded version of the integer. Or same thing, if we have divisions, we can also expand it like this way. And there's also the negative exponent rule. So negative exponent rule, we use this to set the fraction form as the non-fraction form. Okay, so it means if we have exponent as a denominator, then if we change the format of that denominator, then the exponent becomes a negative power. That's what the negative exponent rule means. Okay, then let's try some of the examples. So I'm going to show you how to do question G, H, I, and after these practice examples, you're going to pause the video and then try these remaining 6 examples. Okay, so for the question G, we have 3x times 4 times x squared to the power of 3, right? So in this case, we are first going to simplify what we have inside. So means we're going to simplify our numbers first. So 12 times x2, 1 hidden as a power for the first x, and then 2 with the second x. So 1 plus 2 to the power of 3, right? That's the remaining part of the equation. So it's 12 times x to the power of 3 times 3, and 12 to the power of 3 times x2, 9, right? Because we multiply these two, get this number, and we expand that outside exponent to inside exponents, right? That's expanded power rule. So what kind of rules did I just use? For this one, I used the expanded power rule, and also I use the power rule, right? And for this part, I have used the product rule, right? Then let's try the question H. So for the H, I'm doing 2 times y to the power of 4 over 4y to the power of 2. Then we're first going to separate the numbers from the numerator and the denominator. So the upper part is called numerator, right? And then the lower part is called the denominator. So we are going to separate the numbers first. So 2 over 4 to power 2, right? Because we have to expand the powers to the everything inside of the bracket. Then we have y to power 4 over y to power of 2, right? Then this is same as 4 over 16. And we have a quotient rule inside, so it means we have to do y 4 minus 1, right? Because 1 is hidden in the denominator, and to power 2. So we have 4 over 16 times y to power 3 to power 2, which is equals to 4 over 16 times y to power 6. And we can simplify the fraction or the coefficient, so it becomes 1 over 4 times y to power of 6. That's the answer for the H. Then let's try question I. Okay, you guys must be feeling that I have a lot of steps, right? If you think like you know how to do these questions, you can just skip some of the steps for sure, right? But I'm just doing this or showing these steps for the first timers, okay? So same thing, I'm going to separate my coefficient and expand the power first. And so z over z6 to power of 3. Then this is same as 9 over 8 to power of 3. And z1 is hidden in the numerator, right? So we do z1 minus 6 to power of 3. Then we get 9 over 8 to power of 3 times z to power of negative 5 to power of 3, which is equals to 9 over 8 to power of 3 times z to power of negative 15. Okay, you have got your answer. So at this point, please pause the video and try the question A, D, B, E, C, and F.
A few moments later.
Okay, then let's try the questions together. For question A, we have x times y over 7 x to the power of negative 4 y to the power of negative 2. For this case, let's separate the coefficients first. So this, I'm going to take this one out first. So it's like 1 over 7 times, and I have x times over x to the power of negative 4 times y over y to the power of negative 2. And using the coefficient rule, I can say x1, because 1 is hidden as an exponent for the x. Another one is hidden as an exponent for the y, right? So 1 minus 4 times y to the power of 1 minus 2. I can rewrite it like this, right? Then we have 1 over 7 times x to 5 times y to power of 3. Okay. Then question B, we have 7y to the power of 6 over 4 times y to the power of 5 z to the power of 4. So I'm going to take the coefficient out first. So we have 7 over 4 times y to the power of 6 over y to the power of 5 times 1 over z to the power of 4, right? Because we don't have any other z in the numerator. Then simplifying the y's will be same as y to the power of 6 minus 5 using the quotient rule. Then we get this then it can simplify as 7 over 4 times y to the power of 1 times 1 over z to the power of 5. Okay, then same thing with the question C. We have x to the power of 3 times y to the power of negative 5. 2 times x to the power of negative 4 times y to the power of 2. 4x y to the power of 5. So we first going to collect the like terms, means we're going to take the numbers out first. So 2 times 4, and we're going to take the x's out. So x to the power of 3 times x to the power of negative 4 times x to the power of 1. Even the 1 is not written, we know that 1 is there, right? And we have y to the power of negative 5 times y to the power of 5 and y to the power of 2. Okay, I'm kind of getting out of space, so let's try to keep some space like this. Then we have a times, so we have a product rule, so that means we have to add all the exponents together, right? So x to the power of 3 plus negative 4 plus 1 is 0, and y to the power of 2, right? And using the zero exponent rule, we know that x to the power of 0 is equal to 1, so we have a times y to the power of 2. That we got our answer. Then question D, we have x times w times 6 times x to the power of negative 6 times w to negative 4. First, we're going to take the coefficients out first, so 6 times, and we're going to collect the like terms, x times x to the power of negative 6 times w to the power of negative 4, right? Then we have 6 times, 1 is hidden as exponent for the x and w, right? So using the product rule, we're going to do x to the power of 1 plus negative 6, w to the power of 1 plus negative 4. Then we get 6 times x to the power of negative 5, then times w to the power of negative 3. Then question E, we have w times 4w squared times w squared to the power of 3. Okay, we first use the product rule to simplify the inside of the bracket. Then we get w, so we have 1 hidden as exponent for the first one, right? So 1 plus 2 plus 2, and don't forget the 4, right? 2n to the power of 3. Then we have 4 times w to the power of 5 to the power of 3, right? Then we expand the power, so we get 4 to the power of 3 times w to the power of 15, right? Then we get, I'm not going to expand the 4 to the power of 3, okay? And then lastly, the question F, we have y to the power of square over y to the power of 3, right? So we have bracket and to the power of 3. Using the quotient rule, so we're going to do subtract 1 first, right? To the power of 3. Then we have y to the power of 1 to the power of 3, which is same as y to the power of 3. So I have finished showing you the answer for the example number 1 practice questions. And make sure you check your answers and solutions with mine and see which part you made a mistake, and then try to revisit the laws of the exponents. Okay, then now let's discuss the laws of the logarithms. So before, we have just discussed the laws of the exponents, right? They're very close to each other. So with this section, you will see the two classes or two cases of the logarithms. They're the logarithms in base 10 and the logarithms in base b, where b is a real number. Okay, so this notation here, this notation here is actually our real numbers notation, right? So it's like R with the two like lines, and it means all real numbers. And then when the logarithm has, or the logarithm is in base 10, it is called a common logarithm. And the logarithm in base 10 of a positive number is the power that 10 must be raised to in order to obtain that number. Also, it is agreed that if no base is indicated, we assume it means base 10. Okay, so here we have a symbol log a, right? So when there's no base, usually base goes here, but if there's no base, we say that the base is 10, right? So usually when you're writing the logarithm, you write it as log b to power of a, or the a means number and b means base. Okay, so if base is not written, we say that the base is 10. If the other numbers are used at the base, then we have to identify, such as like log ba. Okay, and also the laws of the logarithm is closely related to the logs of the exponent, and then it can be concluded as in this form. Okay, so if we have exponent b to the power of x, and if it's equals to a, it can be rewritten in the form of the logarithm. Means the base b becomes the base of the logarithm. Okay, the number a, what the exponent equation is equals to, becomes the number of the logarithm. And then the exponent of the exponent equation becomes the what log ba is equals to. Okay, this is how the exponent equation changes its format to the logarithm equation. Then let's try some examples. Okay, so example number 1, we're going to rewrite each equation in logarithm format. So we have equations in exponent equation format. So we're going to change this to logarithm format, right? So we have 16 equals to 2 to the power 4. So the base becomes the base of the exponent logarithm, right? And then the number, or what the exponent equation equals to, becomes the number of the logarithm, and the exponent becomes what the logarithm is equals to, right? That's what you need to remember. Same thing with this guy here. The base becomes the base of the logarithm, right? The number that exponent equation equals to becomes the number of the logarithm, and the exponent of the exponent equation becomes what the logarithm expression equals to, so -2, right? Equation number 2, write each logarithmic equation in exponential form. So we have log base 4 64 equals 3, right? So base is base. What logarithm equals to becomes the exponent, right? And the number becomes what exponential equation equals to. And the number of the logarithm equals to what that exponential equation equals to. So 64 goes here. Same thing here, we have a non-base logarithm form. That means it has base 10, right? So 10 to the power of y equals x, right? Okay, so we have to try the example 3 and 4, but before trying these examples, we're going to visit the laws of the logarithm first. So laws of the logarithm are following. So it's very similar to the exponential rule, but a little different. So product rule, when you can separate the number of the logarithm into like, maybe examples like log b6 is actually same as log b 2 times 3, right? When this happens, you can rewrite this logarithm as log b 2 plus log b 3, okay? That's a product rule. Quotient rule, for this case, log base b a over c is equals to log b a minus log b c. So when we say we have a logarithm with the base b and has for example like 2, but 2 is actually same as log b 8 over 4, right? 8 over 4 is same as 2, so we can rewrite this as log b 8 minus log b 4. So that's what quotient rule means. The power rule. So if your number has exponent, you can move the exponent to the front. Okay. So for example, if you have something like log b to power of 8, then 8 is same as 2 to power of 3, right? When this happens, 3 can move to the front, and this logarithm can be rewritten as the log b or 3 times log b2. Okay, inverse rule, so means log base b times b to the power of n equals n is same as this. Okay, it is possible to prove the inverse rule using the law of the exponents, but we're going to skip for now. Okay, and the change of the base rule means you can change the base of a logarithm using the different base. Means if you have something like log 2 3, okay, log base 2 3, then you can change this base to 10 and then rewrite your logarithm as like this. Okay, that's the change of base rule. And then there's some extras. Okay, means when your number and the base is same, then it is always equals to 1. Or for example, you can say when you have something like base 3 and the number is 3, then it's automatically equals to 1. Okay, and if your number is 1, like this case here, then it is also equals to 1. Okay, then let's try to prove the power law of the logarithm. Okay, because power law will be the one that we're going to use the most. Okay, so let's try to log base x is equal to w. I'm just setting up the like random example, right? So let's let log base x is equal to w. When this happens, we can rewrite w equals log bx in terms of the exponents, right? So like we can change this logarithm format to exponent format. So it means it's same as b to power of w equals to x, right? Then let's try to multiply this exponent format by n, okay, to the exponents, right? So we're going to multiply n to all the exponents of this equation, and this is equals to b to power of w times n equals to x power of n, right? Then if I'm rewriting this to the logarithm format, it is equals to log b times x to the power of n is equals to wn, and we do know that w is same as log bx, right? So, and it has some word n right in front of it. So we have just proved that the power rule makes sense. Then let's try to prove the product law of the logarithm. Okay, in this time we're going to set x equals to log base b m and y equals log bn. Okay, and we're going to change this logarithm format to exponent format, just like the previous process. We're going to say b to the power of x is equal to m, b to the power of y is equal to n. Okay, then multiplying these two together, it will give us the format m times n equals b to the power of x times b to the power of y. Then simplifying the right hand side is same as m times n equals b to the power of x plus y. Then if I'm rewriting this exponent format to the logarithm format, it's going to be same as log b m times n equals to x plus y, which will give us that since x is equal to log bm, y is equal to log base bn, log bm times n is same as log bm plus log bn. So we have just proved the product law of the logarithm. Example number 3, we need to evaluate these two expressions. So question A, log 381. So we do know that the 81 is actually same as 3 to the power of 4 in the exponent format, right? Then using the power, we can move the 4 to the front. Then we have 4 times log 3, and since base and the number are same, this is automatically equals to 1, so we have 4, right? Then question B, log base a to the power of x. Okay, so this one right away we do know that x times log a is happening, right? Then log a is equal to 1, so the final expression is x. Example number 4, we need to solve for the x, right? For these two equations. Since we have to solve for the x, we have to change the logarithm format to the exponential format. Okay, then we have 1 over 3 to the power of 4 equals to x. Then x is same as 1 over 81, right? It's very simple. Then question B, same thing, we're going to change its format to the exponential format. So 10 to the power of 2 equals to 2x plus 1. And we do know that 100 equals to 2x plus 1, which is same as 2x equals 100 minus 1, which is 99. Then x is 99 over 2. Okay, so now let's try the more questions. So here we have example number 5, number 6, and number 7. For example number 5, I suggest that you do it by hand. Number 6 and 7, you can use calculator, but you have to leave your answers to 3 decimal places. Okay, so at this point, please pause the video and try the question yourself and listen to my solutions. Okay.
A few moments later.
So I hope you have tried the questions. So let's start from the example number 5. So we have to evaluate log base 3, 9 to the power of 4, right? So let's say we know that the 9 is actually same as 3 to the power of 2, right? And there's another 4 as power. Then using the law of the exponents, we can first simplify these brackets. So it becomes 3 to the power of 8. Then using the power, we can move it to the front. Then this is same as 8 times log base 3. And since base and the number are same, we can say this is equals to 1. Then we have 8 as the answer for question A. For the question B, we have log base 5 number square root 125, right? For this question, let's try to get rid of this square root because it's annoying. So let's get rid of the square root first for this case, okay? If we change the square root format, we can actually change it to the exponent form, okay? So we can change the square root format to an exponent form. So it means square root 125 becomes 125 to power of 1 over 2. Then using the power rule, let's move the 1 over 2 to the front. Then this is same as 1 over 2 times log 5, 125, which, and then the final answer is 1 over 2 times log 5, 125. But 125 is actually same as 1 over 2 times log 5. 125 is 5 times 5 times 5, right? 5 to the power of 3. So this is same as 5 to the power of 3. Then we can move the 3 to the front. And this is same as 1 over 2 times 3 times log base 5, 5, which is same as 3 over 2. And log base 5, number 5 is same as 1, so it's 1. So the final answer is 3 over 2. Okay, then let's try the example number 6. So we need to evaluate correct to 3 decimal places. We have to calculate this logarithm, or we need to evaluate this logarithm using calculator, right? So log base 5, 17. If you want, you can use add on your function to substitute your logarithm right away, but most of our calculator is not set in that way. Okay, so what you're going to do is you're going to change the format using the different base rules. Okay, so I'm just setting the base as 10, and I separated our logarithm. Okay, then you're going to do using your calculator, you're going to go log 17 divide by log 5. Then you get 1.760, right? Same thing, if you want to substitute this into your calculator, you're going to use the change of base rule to change its format because the calculator doesn't work, right? And then you use your calculator to solve it. Remember, I'm doing this question to show how to substitute different formats of the logarithm into your calculator, right? Negative 3.322. For question number 7, we need to solve for y in the equation 100 equals 2 to the power of y, right? So to solve this exponent format, you first have to change the format of this exponential equation into logarithm equation. We can change its format to log base 2 100 equals y, right? Then solving this part of the equation can give you the correct answer for y. So using the change of base rule, we can substitute the left hand side of the equation into your calculator. So 100 divided by log 2, then we have 6.644 as our answer. Then let's try the example number 9. We need to write following expressions as a single logarithm. Okay, so again, I want you to pause this video and try this question first and restart this video and to check your solutions with mine.
A few moments later.
Okay, so let's try these examples together. So question A, we have logarithms with the base 5 and we have a different sets of numbers and we have positive and negative, right? So it means we're going to use the product rule and quotient rule to simplify this equation. So I'm going to write it here. The product rule and the quotient rule. So first two terms, I'm going to change it as log 6 times 8, okay? And I still have the remaining part, right? Then using the quotient rule, I'm going to change its format to log 5, 6 times 8 over 16, which can simplify into log base 5, 3. Okay. Same thing with the question B. I mean, this is like kind of second step of the change of the base rule, right? So we can just simply do log 2 7/5, right? Then this is equals to, that's it, right? I mean, we can just change its base and we have final answer. Then for the question C, we have base 3's, right? And then we have negative sign in the middle. So means we have to use the quotient rule. So we can do log base 3 405/5, and then 405/5 can simplify it as 81. Okay, then question D. Question D is a little bit tricky because it has a square root. So what you're going to do is you first change the square root forms to non-square root forms using the exponent rules. So you're going to go log square root x is same as x to the power 1/2, as I mentioned before, to power 3. Don't forget that exponent, right? And we have log x to the power square minus log x to the power 1/2. Okay, then we have positive and negative, means we have a product rule here, and we have a quotient rule as the last thing. So we can rewrite this as log x to the power of 3/2. I just simplified it right away, times x to the power of 2, right? Minus log x to the power of 1/2. This is same as log x to the power of 3/2 plus 2 over x to the power of 1/2. Okay, then this is actually same as log x to the power of 7/2, because 3/2 plus 2 is same as 7/2 over x to the power of 1/2. But then it can be simplified as x to the power of 6/2 or log x to the power of 3. And we have 3 times log. So you can either write it as the first form or the second format, right?